Hello Algebra students. Today we're going to look at a special logarithm and a special base for an exponential function. There's two very common logarithms and exponential functions, and those are the common log, in other words base 10, the one where we don't write the 10 as the base, and the natural log, which has a base of e. So I'm going to do just a slight bit of calculus to kind of give you an introduction to where e comes from. E is this ubiquitous irrational number. It's very much like pi. And I'm going to show you a little bit of calculus to show you one place it pops up in nature. It's really special and probably just as common as pi in all kinds of different calculations and equations that you'll be working with. Probably not too much this year, but after this year it just pops up all over the place. So let's begin. So I thought, if you consider this kind of strange exponential function, it's really close to what we were working with. It's got an exponent right here, so that means it's an exponential function. It's got that 1 plus or minus r type of relationship that we saw with exponential growth functions. If it's plus, it's growth, right? Then it's got a strange thing. Instead of going 100% plus a known rate of growth, we've got 1 plus 1 divided by another x. So it's not straight up exponential function. It's something similar, though. So this is what's called a limit. So the way you read this is you say the limit as x approaches infinity. So what I want to do is just use my calculator to graph this function, nothing too high level, and look at the limit as we approach infinity on that function, because that's going to define this special naturalness that we're talking about, and that hopefully you also saw a little bit of in that video on the applications of logarithms with navigation and so forth. So let's have a look at our calculator. So if I graph this function in my calculator, let's see, y equals, alright, so I'm going to go 1 plus 1 divided by x. Just to be safe, I'll use alpha y equals. I'm going to raise that to the x power. Zoom standard. Okay, so here's what 1 divided by 1 plus 1 over x, all raised to the x power, looks like. So what I wanted to do is investigate the limit as x tends to infinity. So as x approaches infinity, I'm going this way. So let's start tracing. So if I hit trace and trace towards infinity, of course I'm not nearly to infinity yet, you can see the y value is getting closer and closer. It's growing, but it's growing really slowly. It's getting closer and closer to a certain value. So I could go to my window and scale the x maximum up much larger, maybe something like that. I don't really need the y max to go as high either, or as low. So adjust my window and look at that function a little more stretched out, and you can see it looks like it actually gets flat. It's not actually flat, it's continuing to increase. You can trace it, and you can see that the y value is increasing as I trace it down here. See, it's increasing down here. So what's it getting closer and closer and closer to? So let's remember that we have this other trick that we could use to try to go closer to infinity as well. Our function is in y1 right now, right? So if I go to vars, y vars function, it's always easy to evaluate the function. So I could look at 100, and at 100 it's that value. At 1,000 it's this value. 10,000 it's this value. You can see it's growing slower and slower as time goes on. In other words, as x values tend towards infinity. It's getting closer and closer and closer to something. If you type E in your calculator, E is over on the right hand side by the raise button underneath clear. You can see that it's tending closer and closer and closer to E. So this is just one place that E pops up. It's usually used as the definition of E, though. So the limit as x approaches infinity of this really special function here goes to exactly E. And you want to memorize what E is just like you know pi. You know that pi is 3.14159. That's probably a good way to remember pi. So E I would remember is 2.718. If you can remember it like that, that's really good information to have for a variety of purposes in this section and later on. So let's do a couple transformations without our calculator now of graphs. So E is 2.718, right? So let's graph the natural logarithm, and before we do that, let's just graph an E exponential function. So ask yourself, is this growth or decay? Since the base is E, and E we just learned is 2.718, well that's more than 1, so it's growth. So this function is growth because the base is E, so we're going to say growth. It's been shifted up 3 because of that 3 outside, and it's been shifted, this is inside, so that's left by 2. So I'm going to sketch it and drop a couple points. So here we go. So remember, exponential functions, we always start with the asymptote if it's been moved. Since it's up 3, it's going to shift the asymptote from 0 up to 3. Now normally, if there's no stretch or compression, which there isn't, it's just e to the x power, then it's going to go through 1 higher than the asymptote, so right there at 4. But that, remember, has been moved by the x plus 2 to the left by 2. So I'm going to go to the left by 2 and move this point right here. If you don't believe it, plug in a point. This is -2. If I plug in -2, I get 0 power. Anything to the 0 is 1. 1 plus 3 is 4. Now, we said this is exponential growth because the base is bigger than 1. So I'm going to draw an exponential growth function. So there's a nice sketch. Probably want to plug in one more point for scale, like maybe 2. So if I plug in 2, what point am I going to get? I'm going to get e to the 4th power plus 3. I guess I could use my calculator for that. Let's see. E raised to the 4th power plus 3 is about 57. So you can see that my exponential growth function is nowhere near steep enough. It needs to be much steeper than that. By the time I get to 2 over here, I should be up at 57. So if that's 4, then this should be going way, way, way faster. So that 2 goes to 57, if you will. All right, let's graph a natural logarithm. So what I want you to be clear about is when I say the natural logarithm of x minus 2, like right here, this is really just the logarithm base e of x minus 2. Your calculator has a button for the natural logarithm because it's the other most common logarithm that's used, but it doesn't look like this, it looks like that. There's all kinds of reasons for that change in notation, but remember, if you see this guy, it just means natural logarithm, or in other words, log base e, so log base 2.718. So this has been shifted because of the minus 2 inside. It's been shifted to the right by 2. Well, what's that logarithm look like? So remember, logarithms don't have a horizontal asymptote, they have a vertical asymptote. We've seen 1 or 2 graphs already, and this is one of the things you want in your library of functions, that logarithm graph with a vertical asymptote at 0, and there you go. This one, though, instead of being a regular logarithm, has been shifted to the right by 2, so that asymptote moves from 0 to x equals 2. And now I've got my nice slow-growing logarithm shape that I'm going to graph. I can plug in a couple points. For instance, maybe I'll plug in 3. If I plug in 3, then I get the natural log 3 minus 2, which is the natural log of 1. And it's key to remember that any logarithm of 1, natural log, log base 10, log base 4, whatever, remember that's e to a power equals 1. What's that power got to be? Of course, that power has to be 0. So there's a point on our logarithm. All logarithms go through 1 away from their asymptote, just like all exponentials go through 1 away from their asymptote, unless you have some kind of stretch or shift or something like that. So I've got a logarithm going up like this. And I'll give it one more point for scale. So let's think what would be a nice point. Let's just plug in something kind of random, like 8. So what's the natural logarithm of, got to put minus 2. 8 minus 2 is the natural log of 6. I'll just have my calculator do that. So press the natural log key on your calculator, and it says that's 1.789, so about 2, so say 1, 2, so at 4, 5, 6, it's about 1.79. So a nice slow growing logarithm. You definitely want to remember that logarithmic shape. Put it in the front of your notes in your library of functions. It's like the 6th or 7th shape we've seen this year. All right, let's look at doing some things like we did in the last section, solving some equations, simplifying some problems with the natural logarithm. It should work the same way. So next I wanted to look at doing some of the same things we've done in 7.4 and 7.5 with this new logarithm and new exponential base. So we're just going to simplify or solve these problems. So let's try to be a little bit quick about it. So in this first one, you've got a logarithm. You could handle this problem two different ways, right? If you've got a logarithm with an exponential inside of it, you can bring the exponent down in front. Or you can just remember that if you have an exponential inside of a logarithm and they're the same base, they're inverse functions, so they cancel. So you know what? I'm going to just do it that way. Say that this is equal to 0.7m. Okay? On the second one, it's pretty much the same thing. You have a logarithm this time inside of an exponential. It's the reverse. But if you have an inverse function inside its partner, other inverse function, then of course they cancel out. The only problem here, and the mistake most students make on this problem on my final exam, is that they don't recognize that that 3 is in the way. 3 is blocking the cancellation of e to the natural logarithm, so you have to move it. The 3, remember though, is in front of a logarithm, so it can be moved. You can in fact go like this. Say that's e to the natural logarithm of x plus 1. That's inside the log. This can move up as its power. And now you have a logarithm inside an exponential. They have the same base, so they cancel. So you get x plus 1 quantity cubed. Or in other words, if you know how to simplify this quickly, like I do, I'll be showing you this next semester, you could write this, of course, as x plus 1, x plus 1, x plus 1, and then FOIL these, and then get that all simplified, multiply that, and FOIL, or excuse me, expand again. It's going to take a long time. You can use a Pascal shortcut to just know what this becomes right away. I know that this is x cubed plus 3x squared plus 3x plus 1. And I'll show you how to do that so you can do it just as quickly next semester. So, alright, that cancels. That's what it is on that one. Let's look at this third one here. So this one we've also got a couple options. You could realize, just like in the first one, that if you've got an exponential with the same base inside of a logarithm, they cancel. That chops and that chops. And you'd end up with 2x plus x, which is of course 3x. You also might recall that if you have one logarithm plus another logarithm and they have the same base, you can write that as one single logarithm using a log property, where you put e to the 2x and e to the x inside, and plus becomes multiplication. So that's the natural log of e. These have the same base. When you have the same base, algebra says powers add. So that's the natural log of e to the 3x. Natural log and e inside of one another are inverses. They cancel out. You get 3x again. So probably easier to go about it the other way. I liked reviewing the rule of logarithms and that rule of exponents as well, so that's why I did it this way this time. All right, let's solve a couple equations. So over here, I think we're going to do just like we did in 7.5, combine the logs first. Minus becomes division inside one single logarithm. Now I need to get inside that logarithm to get x out, so I need to apply the inverse to both sides of my equation. How do you get rid of logarithms? You exponential both sides. What's the base? The base is our new base, e. So I e, or exponential both sides base e, this cancels out. You get x squared over 7 equals e to the 4th power. That's just some irrational number. Don't let it intimidate you. You're solving for x, so times 7 times 7. You get x squared equals 7e to the 4th. And to get rid of squared, of course, we square root. You get x equals plus or minus 7e to the 4th, which is plus or minus root 7, and square root of e to the 4th is e squared. So let's solve one more equation, and then we'll move on to a couple applications. We're going to focus on those a little more in this assignment. So we've got one more equation with natural logs here. So how do we want to do it? So I can't really raise both sides to e to solve the equation yet, because I don't have one logarithm. I've got 3 different terms here. I have a natural log there, a natural log there, and a 5 there. So I think I'm going to subtract this one to the other side. So I'm going to subtract this guy over there. So that's going to leave me with the natural log of x plus 8 minus the natural log of this stuff equals 5. Then I can use a log property to combine those two logs with a minus into one with division. So I'm going to go this guy divided by this guy. And when you divide by a fraction, that's where you employ copy.flip, if you like to remember it from middle school. I always remember that this looks really unstable, and I'm real clear about where my main fraction bar is, because I know I need to flip something here. So I'm going to flip this guy like that, so this x is going to go up here with that. Alright, so now I have my equation into two terms only, and I can operate with an exponential to get rid of the logarithm. So the exponential that gets rid of base e is e. So I exponential both sides base e. Might need some more room here. So this is going to cancel out. We're going to get x plus 8 times x equals e to the 5th. Still got an e to the 4th down there as well. So I'm going to get rid of that e to the 4th. I think I'll multiply it on both sides to get this to look a little nicer. So e to the 4th, e to the 4th. That's going to cancel out that down there, because it was being divided, so I multiplied. So now I've got x squared plus 8x if I distribute. And over here I have e to the, these are the same base, so in algebra we add exponents if they're the same base. That's going to be 5 plus 4, or 9 in other words. Okay, so we've got this guy, so that's going to leave us with x squared plus 8x minus e to the 9th is 0. So we could solve that in a lot of different ways. I doubt it factors, so we're probably going to have to go to the quadratic formula or to our graphing calculator. You know, let's just go to our graphing calculator and see if we can get anything out of that. That's my instinct on this one. So let's see what we've got. I'm going to graph this parabola. So x squared plus 8x minus e to the 9th power. That's a big guy, so I bet zooming, let's see if we can see anything. I couldn't. I'm just going to zoom out. I'm not really sure which way to go yet. I still can't see anything. Remember, e to the 9th power is really big. If you think about it, it's going to in fact be really, really big. So you know, I'm going to move my window to go way far down, maybe 10,000. Oh, not my x value. Let's go, I don't know, let's just stay with 10 to 10 this way and go really far down this way and up quite a ways as well. Well, I'm seeing something finally at least. Ah, I can see a bit of a parabola. I think I can shorten this up a little bit, maybe delete a couple of these zeros, and maybe make the x's go out a little further. There we go, now I'm getting to see a parabolic type shape, so the x's still need to go out further. So there's one of them right there. So second, calculate 0. So on the left side, on the right side, and guessing. So one of my solutions to this parabolic equation is x is approximately 86.106. Now, of course, there's going to be another 0 over here, which we could go find, but it's going to be negative, right? So if you think ahead a little bit, unless that 0 was like -7 or something, -6 or something that would be okay to stick into this logarithm, it's going to be an extraneous solution. And since that's already at 86, this clearly is going to be a really big negative number, which is going to make this negative inside the logarithm, which is going to cause a domain error. Okay? Let's look at a couple applications. So there's two kind of applications I want you to get comfortable with. They're both very common and useful for other classes. So the first one is we're going to go back to money and investment accounts and do a special kind of investment account. This is the way most money accrues interest these days. So it says, how much is a $2,000 investment worth after 10 years? We've got a 2.7% interest rate. And that interest is being compounded continuously. And then we'll ask how long does it take to triple our investment. So first I want to figure out after 10 years. So the key is that this interest isn't being compounded once a year, or quarterly, 4 times a year, or monthly, 12 times a year. Those all have their own special little formula, but all of those formulas pretty much work like the way we've been learning. So you're going to have some initial amount, like a p sub 0, and then you're going to have like 1 plus an interest rate. Now, for different kinds of compounding interest, like this r gets put over the number of compounding periods, then you have an exponent of time up here, and then you have to put an n up there if you're not doing it. So the way we did it before is we just said compound it annually, or once per year, so this reduced to what we're used to. N is 1, then it's what we started out with. If you compound it quarterly or monthly, you have to put a 4 or a 12 in those spots. If this doesn't say quarterly or monthly, it says continuously. So continuously goes back to that function that I was talking about at the beginning, that 1 plus 1 over x to the x. As you approach infinity, that's how you get continuousness. So remember, this thing, as you approach infinity, is e. So you have p sub 0 times e, and then you have that guy up there, so we're going to put to the RT. So this is the formula for compounding interest. It's just like those other kinds of interest problems we did before. If you really understand what I just said, that puts the icing on the cake. If you're not completely sure, that's okay. They're just a bunch of different interest formulas they look really similar to one another. That's good enough for this class. So there we go. PERT is how people remember continuous interest. So now I'm just going to plug my numbers in and see what happens. So it says we've got a $2,000 initial investment. E is E. Interest rate is 2.7%. So that's this. We wanted to see how much it is after 10 years. We can just stick that right in our calculator. So we'll just type that straight into our calculator. So 2,000 times E raised to the 0.027 times 10 years. So after 10 years, their investment's worth $2,600 and some change. All right, the other thing they asked us is how long will it take to triple? So in other words, make this back to a variable t and triple $2,000. In other words, make $2,000 into $6,000. So if you solve for t here, you'll get the answer. So if you divide first, you're going to get 3 equals e to the r t. Now you want to solve for t. This is just a little exponential equation. We get rid of exponentials by using a logarithm. So to get rid of e, I use its log partner, log base e. In other words, the natural log. If I do it to one side, I have to do it to the other side, operating on both sides. So I'll get the natural log of 3 equals, these cancel out, 0.027t. So the last step is going to be t equals the natural log of 3 over 0.027. No graph required. So the natural log of 3 divided by 0.027. So it's going to take about 40 and some years, 41 years about, for us to triple this investment with these statistics. Let's look at one last application before we close up today. So this is a really common one, probably the most common type of application that you do with exponential functions in basic classes. It actually continues into much more advanced math, and so it's really good to know. So how do you do half-lives? Or in other words, how do you do radioactive decay? So it's exponential decay. So for instance, if we were working with plutonium-239, that isotope of plutonium, and they tell us its half-life is 24,000 years, half-life means the amount of time it takes for what you started with to decay to half of its starting value. So we want to know how long it takes for 1 gram to decay to 0.1 grams. So first we have to use that half-life thing. So the whole equation here is pretty similar. I mean, you can call it whatever you want. You can say n instead of p like our book does. You know, I'm just going to stick with what we had before. So we've got an initial amount of our substance. It's decaying all the time, so that's a continuous process. So it's just like PERT instead of a rate of decay. I don't know. I mean, you can call this whatever you want. If you like to call it R, that's fine. You can still go with PERT. Except here this is decay, so instead of growing, it's decaying. So one way to do growth instead of decay, if you've still got to use E, is to flip it, right? With a transformation that flips it this way. So it's really just that same formula working with just the decay version of it. So let's think about half-life. So they said it's half of itself in 24,000 years. So in other words, that 1 will become 1/2 of 1, or 0.5 grams, if you put in 24,000 years right there. That will allow you to solve for R. So this is like step 1. They didn't give us the rate of decay, so we need to find it. Find the rate of decay. You can call it R, you can call it N like our book does, or whatever. What you call it is irrelevant. So I'm going to solve. Really, I don't even need this 1 here, right? So it's going to be just like that problem from a second ago. To get rid of E, I logarithm base E, chop. So now I'm going to have the natural log of 1/2 equals negative R times 24,000. Last step, if I want R, is to take natural log of 1/2, divide it by negative 1, and divide it by 24,000. So that's going to give me my rate of decay. Let's use our calculator. So there's my rate of decay. So it's in scientific notation, so I'm going to write it without that. I'm going to say point negative 5th power for scientific notation, if you remember, is 4 zeros. 1, 2, 3, 4, 2, 8, 7. I better say approximate. So there's my rate of decay. That's step 1. Step 2 is answer the question that they asked you. Once you have your rate of decay, though, that should be easy. So step number 2 is answer question posed. So let's go with what we know. We know that we've got the initial amount, which, oh yeah, we're going to say the initial amount is 1. We know E is E. We know R is that. 1, 2, 3, 4, 2, 8, 7. T is T. And we wanted to really see when 1 gram decayed to 0.1 grams. So this. If you look at this, and you look back to what I had in blue there before I logarithmed it, red logarithm part, it's really like the same exact problem. So the steps to solve it are the exact same. It's kind of redundant. You don't really need this 1 again. If you had it there, though, that's okay. To get rid of E, to bring that power of T down, I'm going to logarithm. If I do it to one side, I do it to the other. So you can see we're doing pretty much the same thing again, except instead of getting R this time, now we'll get T. So the question posed for us was find the time. So this is going to cancel. Our last step is to divide. I'm just going to put that same thing in there. 0.1 here. And negative 1, 2, 3. In fact, you know a better way to do this, since I've got that stored in the column above, instead of typing it in manually, hit second answer, and it'll grab what you had here and load it here, and we won't even have any rounding. So that'll be a lot more accurate. So there we go. One thing. I should have put second insert, negative second answer. So let's go back and do that again. So back up here, let's delete this step. Go back to here, and I'm going to say natural log of 0.1 divided by, and see that answer was positive, so I'm going to have to put a negative in myself and then say second answer. There we go. That makes sense. So we're going to get 80,091.687. And remember, what are units here? Our units are years. So this is why weapons grade plutonium, which is what Pu-239 is so dangerous. Now, oil companies and so forth will use this to try to scare you, because they'll say, wow, it's going to take 80,000 years or hundreds of thousands of years if there's some kind of nuclear accident at a nuclear plant. Remember, this is nuclear weapons type of plutonium. It's not the same kind of uranium or radioactive products that nuclear power plants use. Most of the products in those plants decay at a much faster rate. But it's quite a complex idea. But here you can see how to work with radioactive decay of all kinds of different particles and isotopes, not just plutonium. So I'll conclude there. Make sure you finish up your assignment and that worksheet, and we'll grade those on Monday when we get back from Thanksgiving. Have a wonderful break, you guys. See ya.